Welcome to AP Calculus Self-Check 8.7 and 8.8. Let's jump right in. Today's date is February 10th, 2022. All right, in this problem, oil is leaking into the surface of a lake, and it's going to make a right circular cylinder. So if I were to draw a picture, I'd like to zoom out here. Essentially, I have this picture of this cylinder like so. I always draw a picture when I see a problem that tells me a shape. And what do we have? Let's go ahead and identify. And part A is kind of weird. It looks like it's a related rate problem, and it is. But then B and C kind of relate more to Unit 8. So right at the beginning, it tells us that the volume is increasing at 2,000 cubic centimeters per minute. Units don't matter so much for this first part, but I'm going to go ahead and say that that is our V prime. Is it going to be a positive or a negative 2,000? Well, it says increase, and that is a word that means a positive amount. So this is going to be just a positive 2,000. What else do we have? Reading, good. It gives us a formula, which we'll probably use. I'll write it out here. A formula that is pi r squared h. What else is given to us? It tells us that the radius is 100, so we're going to say r is equal to 100, and very rarely will they shift units like, say, millimeters or something like that, where we have to multiply or divide by 100 or 1,000. Height is 0.5, so we'll say h here is going to be 0.5. And it says that the radius is increasing at a rate. So this is not talking about r anymore. It's talking about r prime. And increasing, again, is this positive word for increasing at 2.5. So it's going to be a positive 2.5. And I think we have everything. What are we after? We're after the rate of change of the height. We're after an h prime. H prime is going to be our question mark, our empty box, the thing that we're after. So right away, I noticed that it's giving us v prime, r prime, and asking for h prime. We need to take the derivative of this function. We might use v later, so maybe I'll leave it there for later. I don't know. I haven't seen this problem in a while. And we'll say v prime. So I'm going to take the derivative of the left. We'll use a new color for the derivative. If I take the derivative of the left, it's v prime. Easy. All right. The derivative of the right. Notice I have two variables here, r and h. So I'm going to be using product rule. The way that I typically do product rule is I think of the pi as factored out. I'm only going to do product rule of the inside. So here I'm going to write the pi. And here we go. So I'm going to do 1 d2. 1 is this r squared. d2, well, the derivative of h is h prime. So I have r squared h prime. And then I'm going to add 2d1. 2 is h. And that's going to be multiplied with the derivative of r squared. Again, this is with respect to time, so none of these variables are what it's with respect to. So this is going to be, the 2 is going to come down in front. I'm going to have an r. And don't forget about your dinner. The derivative of r is your r prime. We didn't have to worry about dinner for h because there was no dinner. There's no inner function. We're inside of a house here. There's no house over here, so that's why we're worrying about it. All right, we have our function after we take the derivative. Let's start just plugging things in. Maybe we'll just get lucky and have this done in one step. Notice that I have a 2,000 I can plug in for v prime. So I'm going to say 2,000 is equal to, I'm going to leave that pi factored out. I'm not going to do anything fancy here. R squared. Well, r is 100, so that's going to be plugged in for this r. I'm going to have 100 squared. Maybe I can make that square yellow so you know it's still there. H prime. Hey, that's the thing we're looking for, h prime. So I'm going to leave times h prime here. Plus an h. H we do know. H is 0.5. So I'm going to say 0.5 times that original 2 in the equation. And then we have an r prime. So r we have is 100. So I can say times 100 times r prime. R prime is 2.5. So I can say times 2.5. Excellent. And then that ends our parentheses. Maybe I should have made this parenthesis and pi yellow or orange, whatever color this is. Excellent. So I think we are done. We have only one variable, and we can just solve. Yes. All right. We never had to use that blue equation. Hooray. Let's zoom in here so it looks like I have better handwriting when I zoom back out. Let's go ahead and simplify, shall we? On this right side, we still have that pi. We'll deal with you. Actually, let's deal with the pi right now. I'm sick of it. Let's get rid of it. So I have 2,000 divided by pi. I divided by pi on both sides. That's where the pi went. And then over here I have 100 squared. Well, double the amount of zeros here. So I have, instead of 2 zeros, 4 zeros. So 1, 2, 3, 4 zeros. And that's going to be times h prime. And then all of this stuff. The cool thing about 0.5 and 2 is when you multiply them together, 0.5 times 2 is just 1. So they're basically gone. And all I have is 100 times 2.5, which is moving the decimal place 1, 2 to the right. That's 250. 250. Excellent. I've simplified quite a bit. Solving for h prime. Let's get rid of the 250 first. Hopefully you're okay following the work I'm about to do. I'm going to subtract 250 on both sides, which gives me a 2,000 over pi minus 250, which is now going to be equal to this 10,000 h prime. And finally, we're going to divide both sides by 10,000, and I get h prime by itself. H prime by itself is equal to this 2,000 divided by pi minus 250. And I could combine those two if I wanted to. I should note, I could multiply by pi over pi and combine this into one fraction, but I'm going to be lazy, and I don't have to. So I'm just going to say, hey, that's just divided by 10, 1, 2, 3, 10,000. And that's my final answer. Excellent. And I guess I might want to have units on here. It doesn't say to, but my units would have been, since this is h is a change of height, which is in centimeters. It would be centimeters and then prime, centimeters per time. What was our time here? Centimeters per minute. So our units could have been, I'll zoom back in here. This could have been centimeters per minute. But you didn't need to have that. You don't get points taken off of that. Speaking of points, come on, let's zoom back out. How many points do we get for this thing? According to the scoring guide, this is from 2008, by the way, the exact question. You get 1 point. Why am I so far zoomed out? There we go. You get 1 point if you somehow mention that v prime was 2,000 and that r prime was 2.5. So literally for saying this and this, you get 1 point for just saying those two. Excellent. You get 2 points if you have an expression for v prime. Well, I'm interpreting that as, hey, if you got this equation of v prime, give yourself +2 for that knowing it was product rule. I'm maybe like +1 for that piece of the product rule, +1 for that product rule, that piece of the product rule. Maybe that would be the interpretation. Maybe you could get partial points there. And then 1 point for the answer, which they somehow figured that out without a calculator. I mean, this is problem number 3. Again, questions 1 and 2 are always with a calculator. Question number 3 through 6 are not with a calculator, so I'm very confused on how we were supposed to get that. All of this gross stuff. Okay, whatever. It said 1 point for the answer. So we're going to come back up here. Whoa, what? Why is it doing this? Thank you. I'm going to say just +1 point for the answer, and that's going to be out of 4 points. Excellent. All right. Part B, a recovery device arrives on the scene, begins removing oil. All right, so what's happening here is what we have, the volume is increasing. So this is a positive function. It's essentially saying we have a positive function of 2,000. And then we have this negative function that is actually having a variable in it, 400 square root of t. And what does it want us to, so it repeats the information. We still have that's a positive right here of 2,000. And we have to find the time t, not the amount, just the time, it says, when it reaches the maximum volume. Okay, so we're looking for a max. Generally speaking, a maximum should always be a table. But a table is usually reserved for when you have a calculator. So it would take way too much work to do this if we don't have a calculator. There's got to be a better way. And in fact, there is. So let me go ahead and make this equation that is the total amount of oil. Maybe I'll just call this O of t for oil. The total amount of oil, the change in oil is the positive minus the negative. It is 2,000 minus the negative, minus this 400 square root of t. So pay attention to our units here. We're looking for a volume. This is kind of like, I'm doing air quotes right now. That's kind of like position. All right, position under this, POS. Not piece of, but it's position. So if it's asking for a max position, we need to take the derivative of this thing and then figure out where you change from a positive to a negative. Essentially, I'm asking, what is the old-fashioned definition of F relative maximum? And then you guys will all respond in unison. Ah, yes, that's where you take the derivative of the thing I'm talking about. You take f prime and you figure out where it goes from a positive to a negative. So take the derivative of the thing I was talking about. I'm talking about volume. So I must have to look at the rate of the volume. And hey, this equation right here is the rate of the volume. I'll type that here to remind ourselves in a slightly smaller font that this is equation for the rate of the volume, rate of the change of the volume, I guess. That's what we just wrote right here. So what we have found, this is f prime. This is the thing we were after. We just need to figure out, where does this thing turn from a positive to a negative? If you don't know this thing, if you have a thermometer and you go from a positive to a negative, you have crossed zero. So if we set this thing equal to 0, we can identify where that transformation from a positive to a negative occurs. So let's do that. Let's go ahead and say, yes, this 2000 minus 400 root t. Set that equal to 0, and we can find where we change from this positive to a negative. I'm going to add 400 root t to both sides. I don't know why I'm showing my work. I could have just said that and you would have followed that, but I'm adding that to both sides, and I now get this new equation. 2000 is equal to 400 root t. Excellent. Divide both sides by 400. I'm just going to write my new equation in green. I get 2000 over 400 is equal to square root of t. I can simplify a little bit because there's this cool thing when you have zeros on the top and the bottom. Just cross off one per, and I get now 20 divided by 4, which is just 5. So 5 is equal to the square root of t. How would I isolate for t? How do I undo a square root? You square it. So I'm going to square the right-hand side of the equal to sign, square the left-hand side, and I get 25 is equal to t, which is the thing I was after. I was only supposed to find the time t, and I have found the time t at 25. However, that is only where it is equal to 0. I need to verify that it is from a positive to a negative. I mean, it's an AP question, so there has to be an answer, and we only found one answer. If I found two answers, maybe I could eliminate one of them and be like, that's a critical value, but not a relative extremum. It doesn't actually switch signs. The graphic comes down and it touches, and then it turns around right here. But there's only one answer. We could have just been satisfied saying, yeah, the time is 25 minutes, and we'll just give the definition because it changes from a positive to negative, and then we would get full points. I'm going to verify it. I'm going above and beyond here. But I think you might have to do this on your test. Is there a scoring key? Does it say? It says justification. So how will you justify that? Well, I'm going to justify my answer with this number line and say it is indeed a relative maximum because at 25, that we have a critical value. So what's a number to the left of 25? Like 0. 0 is to the left. And when I plug in 0 to this equation up here, notice that 0, the square root of 0 is 0, and 0 times 400 is 0, and 2000 minus 0 is 2000, but I don't care that it was a number. I care that it was a positive 2000. And guess what's about to happen? It's going to turn from a positive to a negative. I can preemptively say it's a negative, but just to be sure, let's just plug in like a big number, like 100. Not 1,000. 100. 100 is a nice number because it's a square number, so I can easily square root it. The square root of this 100 is 10. And then 400 times that 10 is 4,000. So this right here is 4,000. 2,000 minus 4,000 is negative 2,000, and the key word being negative. It does indeed switch from a positive to a negative at 25. This is the work that shows that, and I can make my final conclusion in words that, what are we saying? The oil slick reaches its, why is this all squished? Come on, computer. You're smarter than this. You're better than this. Reaches its max at t is equal to 25 minutes. Do you need units? No. But should you use them? Yes. You should always be using units whenever you can. How would you score this thing? Did you somehow say that r of t was equal to 2000? They said it right here. When r of t is equal to 2000. Well, we said that right here. This is r of t, right? R of t, see? And we set that equal to 2000. So at this point, when you get to right here, you get a +1 when you set those two equal to each other. Cool. I mean, if you said this right here, I would give you the point. Did you get the right answer? Did you get t is equal to 25? You get +1. Even if you took a shot in the dark and just like it was 25. So like by this time down here, you would have got your +1 point without justification. Here's the justification why it's a relative extrema and thus the maximum. There's only one maximum and it happens at the relative extrema. There it is. So that's your justification. And I guess what we should have done to really lock in our justification, because this is where I could just say because the rate changes from a positive to a negative. And you could say the derivative instead of the rate, because this is the derivative. But I like using the word rate because this is the equation of rate. And I know that that is really derivative. So I'm going to say +1 is for this justification and really for this justification down there. So it's for both of them. I heavily justified it. Do you need to do that? I guess not really, because you have this table that is saying basically the same thing down here. You have to do one of them to get your point. All right, part C. By the time the recovery device began removing oil, 60,000 cubic centimeters have already leaked. Come on, guys. Why were you so late? Right, but don't evaluate. Oh, thank God. I love these questions. Do not evaluate. Less work for us. An expression involving an integral that gives the volume, not the rate of the volume, but the volume of oil found in part B. Oh, so if you didn't solve for part B, you're totally out of luck in part C, aren't you? All right, well, because I'm after volume and I have this cool little equation that gives the total change in volume, I'm basically going to say, hey, this equation, I'm going to take its integral since that's its rate of the oil. So essentially what I'm saying here is I'm doing a start plus a change to get my end value. What is our start? It tells us our start right here. Our start is there's 60,000 cubic centimeters, which again, it can be abbreviated as CC for all of you that are going to be doctors. CCs of oil. So our start is 60,000, 60 with 4, or I guess 60 with 3 zeros, or 6 with 4 zeros, plus the change. The change is going to be an integral. It did say to use an integral, right? The integral of this equation that we found up here, this 2,000 minus 400 square root of t, plus this 2,000 minus, what was it, 400 root t, 400 square root of t. All of this thing, dt. All right, and that's our end. We're done, except for the fact that we don't have bounds on our integral. What are our bounds? Well, I assume when you get there, you start. So at time equals 0. And how long does it take to get to part B? Well, in part B, we found t was 25. So 0 to 25 from part B. And now we're done. How many points are we at? I totally forgot to total up the points that we got up here. That was out of 3. Out of 3. This one must be out of 4, 5, 6, 7. This one must be out of 2 to add up to 9. Out of 2. Where did they come from, scoring guide? It says 2 if you got the limits, 0 to 25, and initial condition. So there's 1 point. And the other point comes from the inside, also known as the integrand. So I'm going to come back over here and do the same thing. So all of you, including the bounds, was plus 1 point. And all of you, the inside, including the dt, theoretically, that's technically part of the integrand, is plus 1 point. Cool. And that concludes self-check 8.7. Let's jump into 8.8. All right. Calculator question, which is perfect because I actually have a calculator. Because this is recorded in 2022, I'm using this justified version, and just to put that up on the, this is the URL that I'm using. It's chematech.net. I don't know, whatever. There it is. You have to have your own ROM file, but it's still really nice. Reading the question. Between 9 a.m. and 9 p.m. it enters. All right, so let me zoom in so I can have like a slightly better handwriting here. It enters. This is a positive rate. That means this function is a positive function. And because we have a calculator, let's go ahead and just enter this thing. Y is equal to, it's going to be 73 with 1, 2, 3 zeros divided by, okay, all of this needs to be in parentheses, otherwise it's not, the order of operations will mess you up. You do need this x squared minus 8x plus 25. You don't have to end the parentheses, but I am because I'm cool like that. All right, we have our equation entered. Oh, it tells us our window between 0 and 12. I don't know if we'll need to graph this, but 0, enter, 12, enter, might as well, right? Okay, so I have the window correct. Coming back here, what else we got? Zoom out, Mr. Snell, so I can read. Blah, blah, blah. Oh, whoa, this is really weird. It tells us the starting amount right here, which is not the weird part. It tells us that this is the starting amount. It starts out with 500,000 gallons of water at 9 a.m. But the weird part is it tells us the end amount, which is normally it doesn't ever tell us. Normally we're trying to figure out the end amount. This is both the start and the end amount. So something happens to where maybe like there's less water and then you end up with the same amount of water, right? Weird things. All right. What is K? I didn't read the question. What is K? Pumped out. Oh, pumped out. That's a negative rate at a constant rate of K. Okay, so our equation is K. It's a very simple equation. It's y equals K. Wow, very hard. But that is our negative function. Okay, well, again, whenever I have a positive and a negative rate, just subtract them, right? So I'm going to say that I'm going to give myself some room because I can kind of predict what's about to happen. What I'm essentially doing is I'm saying, hey, start plus change is equal to end. I'll go and give you that hint. And the change, we know that is just going to be, it's going to be an integral, but I'm going to do my positive function, my capital R of t, and I'm going to subtract my negative function, which in this case is just k. That is the positive minus negative, and if I do the integral of those rates, it will represent the total amount of change. And guess what you're going to integrate it between? You've guessed it, it tells you the bounds up here between 0 to 12. And if you had to manually calculate, 9 a.m. to 9 p.m. is 1, 2, 3, 4. Yeah, it's 12 hours. It's 0 to 12. Excellent. And what was our start amount? It was 5. Oh, come on. I got weird lag here. 500,000. And what was our end amount? 500,000, which is a little bit awkward, right? But there it is. Okay, we set up our equation. And notice that this thing has to be 0 because 0 plus 500,000 is 500,000. So essentially what I have just said is I have converted our equation into a cooler and more solvable equation. The integral, come on computer, the integral between 0 and 12 of capital R of t minus k, I guess I should really be formal about this and have a dt. I wasn't very formal over here, was I? This whole thing, dt, that is equal to 0. It has to be for this equation over here to make sense. And guess what I can do now? I can separate this into two different integrals. I can say, hey, the integral between 0 and 12 of capital R of t dt minus this integral from 0 to 12 of k dt has to be equal to 0. It's helpful to be able to separate integrals. You're allowed to whenever there's a minus sign here. And guess what I'm going to do now? I'm going to add this integral to both sides. And when I do that, I get my original integral, 0 to 12 of capital R of t dt. And on the right-hand side, I have a positive version, 0 to 12 of this k dt. dt. No more 0, right? So now you might be a little bit stuck, but just remind yourself, k is a constant, which is always funny. It's a constant rate of k. K for constant, right? You don't spell constant with a C, you spell it with a k. Right here, a constant amount. So if it's a constant, that's a fancy word for a number. This number is like 5 or 3 or just some number, right? So if it's a number, we can use the shortcut on it. And here is the shortcut. The shortcut is you subtract the bounds, 12 minus 0, and then you multiply it by the number. The number is k in this case, k for constant. And now there's no more integral, and over here I have this same R of t dt between 0 and 12. And by the way, I should mention, this is something that the calculator can handle. It can handle doing the integral of capital R of t because R of t is literally an equation that we already have in our calculator. And notice that this over here on the right-hand side is 12k. So What do we do to solve for k, kids? Well, we divide both sides by 12, Mr. Sindel. Yes, kids, you are so smart. And we've solved for k. You can come back over here. I know I kind of moved into part B here, but k is equal to this integral between 0 and 12 of capital R of t dt all over 12. The calculator just punches this into the calculator and you're done. However, I want to pause and just ask the question, doesn't that look familiar? That's the equation of a speed sheet definition. Come on. It's, yes, average rate. It's the average rate of R of t, which makes sense because if I take out the average rate as it moves in, the in and out cancel out over the course of that 12 hours. It's kind of nice. Anyway, jumping over here, turn back on, wake up. I'm going to do my math 9 integral between 0 and 12 of my vars right, enter my y1 with respect to x, and then I'm going to divide it by 12, all in the same step. You could do it in one step and then the second step. You can do it 2 steps, that's fine. I'm going to do it all in one step because I'm cool like that. And so this will be a little bit different for everyone in terms of your decimal, I think. And that's why they tell you right here to round your answer, because they know that the decimal is going to be a little bit off for every calculator, depending on the model of calculator. So we can say that is approximately, we can say that k is approximately 4,338.067. You'll get a slightly different answer, but because we're rounding the nearest whole number, k is 4,338 gallons. GAL is the abbreviation for gallons there. Excellent. And I don't have an answer key for this, so I'm going to do points at the very end. I'm going to try to make sure that they add up to 9, but there it is. There's the answer. And wait a sec. That's not gallons. I'm thinking about the units because I was thinking like that's an average rate, right? I just told you that was an average rate. Well, that's not a rate. That's an amount. It's gallons per hour, Mr. Sindel. Gosh, get on it. There it is. Okay, gallons per hour. Average rate, gallons per hour. Whew. All right. B, to the nearest gallon. Again, rounding to the nearest gallon. Thank you. How much water is in the reservoir at 7 p.m.? Okay, so it's doing the integral between not 0 to 12. Back over here is 0 to 12. It's 0 to 10. And the problem with this is you had to have solved part A to be able to solve part B because it relies on K. Again, we're essentially doing this exact equation, but it's like, hey, you figured out what K is, so go ahead and plug it in, right? So again, we're looking for an end amount. So it's going to be our start. I guess we can have like a T value column, right? So here, let me move things over a little bit. We can have like a T value. We can do, come on, my computer can't keep up with me. Start plus change is equal to the end amount, which we are after. What is the end amount? Well, the time is T. Oh my God, the time is T. The time is 10, and I had lag there. Double wombo combo. The start is still 500,000. Please don't forget that. You'll definitely lose a point. And the change is that exact function up here. It's this integral of 0 to, guess what value? Not 12 anymore, but 10 of capital R of t, but not minus k, because we know what k is. I guess if you're lazy, you could just write k again. But I'm going to be cool about it. I'm going to say 4,338. 4,300, oh wait, 38. So now there's the question, like, wait, Mr. Sindel, do we use a rounded version or do we not? I'm not, because k is exactly that, and it told us to round to the nearest whole number, but that's not really what k is. I'm going to say 0.067, 0.067. And then all of this thing, dt. And that will, again, we'll get an approximation to that. Type this into the calculator and you got it. So before I do that, I want to show you how to store answers on the calculator. I want to store this exactly, the 0.6067329, including all that, so we don't even have to enter this in. It'll be stored exactly. The way you do that is you click on the store, and then you get to choose a letter. I'm going to choose, I could do A, but I'm going to be cooler than that. I'm going to choose K. Where's K? LMNOP8, there's a K, there it is, K. I'm going to do the alpha K. I could have stored it to A. I'm just being cool. There it is. I'm storing it to K. So now if I come back here and I hit second enter, I can do, actually I don't want to do that. I'm going to do it from scratch because I want that initial amount. 500, 500,000 plus math 9 to do the integral. The integral between 0, not 12, 10. Okay, now there's going to be a bunch of things in here. It's going to be vars right, enter, y1, and then I'm going to subtract k, which is alpha parentheses. minus k, and that's minus that 4,338, blah, blah, blah stuff, right? And with respect to x, of course, thank you. And my calculator will spit out a number, which, again, it will be a little bit off, depending on the calculator and depending if you store your answer and a bunch of things. That's why they tell you to round your answer. And there it is. So I'm going to come back over here and say this is about 506,124.129. But again, the decimals don't matter at this point, because rounded to the nearest gallon, that is 506,124 gallons. Why didn't I just write gallons like this? I don't know. I was being weird. Cool. That's it. Let's move on to the harder question. Here we go. At what time t does the reservoir hold the greatest amount of water? Okay, we're looking for a max, kids. Greatest, that's the word meaning max. We need a table. All right, let's go ahead and set up a table. Shoink, t. All right, start amount, 0. Come on, computer, keep up with me. 0, 12, and, oh my God, come on, computer. And any relative extremums are going to go in here. Did we ever find? We never found relative extremums. How are we going to do that? Well, let me show you a cool little trick, guys. Because if you come here to the calculator and zoom 0 this thing, you'll be like, wait a sec, Mr. Sindel, this function just fluctuates up and down and it never actually touches the t-axis or the x-axis. It is t-axis. The t-axis. Well, I will show you that's because we are entering this function right here and not this function right here. So what I'm going to do is I'm going to come up here to my y equals. I'm going to go hover over the equal to sign and hit enter so it doesn't graph that one anymore. For y2, I'm going to say this is vars right, enter, enter, my y1 minus my alpha parentheses, minus my k. And now if I zoom 0, check this out. Now it will touch the t-axis, and it touches it twice. Do you need to have both of those in there? I mean, you can brute force it, but remind yourself that the definition of we're doing a maximum, right? Yeah, a maximum, not a minimum, is a change from a height from a positive to a negative on the graph of velocity. This is the graph of velocity since this is a graph of rate and we're looking for an amount of water. So I'm interpreting this graph as the derivative. Where do I switch from a height from a positive to a negative? Well, at that point right there. So let's find what that is. It's going to be second calculation to do trace. We're looking for the 0, so 2. Left bound, I don't know, like 5. Let me guess, like 8. And let me guess, like 6. It's probably a little bit bigger than 6. Yeah, 6.798. 6.798. So come back over here. 6.798. I'm excluding this critical value over here because it's a relative minimum. A minimum can never be a maximum. As hard as she or he may try. Sorry. All right, so coming back, we're going to say start plus change is equal to the end value. And it's going to be a little bit silly to do this because we know that the start amount is 500,000 for all of these. I'm just going to be lazy and I can just copy paste this. Well, I thought I was going to be lazy, but my computer is going to go slower than if I had just hand wrote this. Come on. Handwrittenness? What is the correct past tense of right? I'm not an English person. I'm apologizing. But the reason that this is silly is because at the end of that 12-hour period, we also know it's going to be, copy paste, 500,000. Which means this start amount and end amount are both 500,000. The only answer is going to be right here. So the only integral I really need is this. Oh, did we turn on? There we go. Is this integral over here, this plus integral of, what is our function? R of t minus 4,330, all of that thing. So it's going to be capital R of t minus, I'm just going to call it k because I'm going to be lazy, but the AP grader knows exactly what that is. And the bounds are going to be between 0 and 6.79. Come on, computer. 6.798. I do want this key to look a little bit nicer. 8. All right, so coming back over here to the calculator, we're going to clear second mode to quit out of this thing. We're going to do, it's basically that same integral, so I'm going to hit second enter and come back over here and change the 10 to a 6.798, and we get our answer as coming back over here, 511,337.936. Again, because whenever you do integrals of these large amounts, your calculator won't have the exact same decimals as I will. Fine, I'll write these integrals too. 0 to 0 of r of t minus k plus the integral from 0 to 12 of r of t minus k. And there's our final answer. And it's going to ask for just the time, because if it was asking for this final amount, it would ask us to round to the nearest whole number. So our final answer, let's write with words. We will say the maximum is at time 6.798. What is our time unit here? You don't need to have units here, but I should just be practicing per hour. So it's going to be hours with 511,337, we'll call it 338 gallons. Do you need to have the 511,000 gallons? No, you don't. All right, so I did promise at the very end that I would go back through and figure out how to score all this stuff. I do want to add it up to 9, so I'm going to do it on the fly here. Let's say if you got the final answer, which you only needed time, you didn't need the 511,000. I'll give you 1 point if you got the final time. I'll give you 1 point if you even considered the time 6.798, and I will give you 1 point of the justification of that. How do you find the max? So for all of us, that would be a table or some explanation plus 1. All right, so that means that one would be out of 3. This one, let's make it out of 4 points. I'll give you, my computer's lagging here. I'll give you 1 point if you got an initial value. We'll give you a whole point if you got the bounds. I'll give a whole point if you got the integrand, aka come on computer, the integrand, aka the inside part. Oh my god, plus 1. And I'll give you 1 point if you got the final answer. It has to be rounded. This one is not the point. This one down here is going to be the point. That does add up to 4. 3 plus 4 is 7. I need 2 more points up here, and that actually works out perfect. Divided by 2, out of 2. You have to set up the equation. So if you set up the equation like this, you set the integral equal to 0, I'll give you a plus 1. And if you get the final answer with the rounded 4,338, I will give you another plus 1. All right, that adds up to 9. Add them both up in the top right-hand corner. Out of 9 points, how many did you get? If I didn't have computer lag, that would also be nice. Why is that not going? There it goes. All right, and thank you for watching. That was a long video. I'll see you guys later.